You hear about comets all the time. Icy chunks from our own solar system, predictable orbits, water vapor tails. But on July 1st, 2025, astronomers spotted something that broke every rule. An object moving at 61 kilometers per second, coming from the direction of Sagittarius, not bound to our sun, the third confirmed visitor from another star system. They called it 3I Atlas, the third interstellar object ever discovered. And from the moment telescopes locked onto it, nothing made sense. If you value documented space discovery stories like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from NASA's official 3I Atlas mission page published July 3rd, 2025, Avi Loeb's peer-reviewed papers from Harvard Smithsonian Center for Astrophysics, and observations from the James Webb Space Telescope reported August 6th, 2025. Now back to the information. 4.5 astronomical units from our sun when first detected. That's 670 million kilometers out, beyond Jupiter's orbit. At that distance, most comets stay frozen solid, dead rocks in space, but 3I Atlas was already glowing, already active. NASA's test satellite caught it with a coma back in May 2025, when it was 6 times Earth's distance from the sun. Water ice can't sublimate at that range. Something else was driving its activity. The size estimates kept changing. First, 20 kilometers across based on brightness. Then Hubble narrowed it down to between 320 meters and 5.6 kilometers. But SphereX observations suggested something massive, 46 kilometers in diameter. If solid, west. That's 1 million times more massive than the previous interstellar comet 2, Borisov. The math doesn't work. We should have spotted 1,000 objects like Borisov before finding one giant like this. The James Webb Space Telescope trained its infrared eye on 3I Atlas August 6th. What it found defied every expectation. Carbon dioxide dominated the coma, 130 kilograms per second of CO2 outgassing. Water? Just 6.6 kilograms per second, 5% of the carbon dioxide output. No comet in our solar system behaves like this. Comets are water-rich. This thing was breathing industrial levels of carbon dioxide. Then came the chemistry reports from Chile's Very Large Telescope. Cyanide in the gas plume. Nickel without iron. In nature, iron and nickel form together in supernova explosions. They appear together in normal comets. But 3I Atlas was pumping pure nickel into space. Industrial nickel production creates nickel without iron. Natural processes don't. The orbital mechanics raised more questions. 3. I Atlas follows a retrograde path within 5 degrees of Earth's orbital plane. The probability of a random interstellar object hitting this narrow ecliptic window, 0.2%. It will pass within 0.19 astronomical units of Mars on October 3rd. Close approaches to Venus, Jupiter too. The cumulative probability of such a planetary survey pattern, 0.005%. Harvard astrophysicist Avi Loeb published papers suggesting technological possibilities. On his scale, where 0 means definitely natural and 10 means definitely artificial, he rated 3I Atlas a 6, then raised it based on new data, the trajectory alignment, the industrial chemistry, the eclipse timing. October 29th, 2025, perihelion. 3I Atlas will pass behind the sun from Earth's perspective, hidden from our most powerful telescopes during its closest solar approach, perfect conditions for what Loeb called a reverse solar Oberth maneuver. A braking technique that could capture the object into our solar system permanently. But the tale told a different story. August 27th, Gemini South Telescope in Chile captured something crucial, a 56,000 kilometer tail stretching behind 3I Atlas. Pointing away from the sun, anti-solar direction, southeast in the sky. Exactly what you'd expect from solar radiation pressure-pushing dust particles. Normal cometary behavior, finally. The coma showed fan-shaped structure. Brighter on the sun-facing side where ice sublimation occurs fastest. Very large telescope images from July to August documented the evolution. Early observations showed a sun-facing plume of ejected material. By late August, the classic anti-solar tail had formed. The teardrop shape matched theoretical models of gas plumes shaped by solar wind pressure. Distance revealed scale. The carbon dioxide plume mapped by SphereX extended 348,000 kilometers around the nucleus. Ram pressure calculations showed the solar wind balancing the CO2 outflow at exactly that boundary. Physics, working as expected, no mysterious orientations, no perfect sun-facing configurations. The speculation reached fever pitch in online markets. Polymarket opened betting on whether 3I Atlas was natural or artificial. Social media buzzed with alien mothership theories, mini-probe release scenarios, dark forest hypothesis discussions, but each new observation strengthened the comet identification. Hubble's sharpest images revealed the classic dusty coma structure, particle size distribution consistent with sublimating ices, reflectivity matching carbonaceous chondrite material. The broad tail appearance suggested high-speed dust ejection, normal for distant comets activated by carbon dioxide rather than water. Pre-discovery data extended back to May 21st, 2025. Multiple observatories confirmed the hyperbolic trajectory, eccentricity 6.141 doors, the highest of any known interstellar object. Faster than 1, Oumuamua, or 2 Borisov, moving too fast for our sun's gravity to capture it permanently. The timing played tricks on perception. 3, Atlas, approached from the direction of the Milky Way's center. Dense star fields made early detection nearly impossible. A natural explanation for why it wasn't spotted sooner. No deliberate concealment, just bad astronomical luck. Mars Reconnaissance Orbiter prepared for close encounter. Imaging. October 3rd flyby at 28 million kilometers. High rise. Camera resolution of 30 kilometers per pixel. European Space Agency's Mars, Express, and ExoMars Trace gas orbiter joining the observation campaign. The chance to photograph an interstellar visitor from another planet's perspective. Chemical composition analysis continued, revealing surprises. Carbon monoxide at 14 kilograms per second. Carbonyl sulfide detected in the coma. The highest carbon dioxide to water ratio ever observed in any comet, but ratio extremes don't equal artificial origin. They suggest formation conditions in a different stellar environment. Temperature calculations showed the mystery dissolving. At 6 astronomical units, solar radiation intensity drops to 1/36th of Earth's level. Water ice stays frozen. Carbon dioxide and carbon monoxide sublimate at much lower temperatures. 3I Atlas activated early, because it's made of different ices than solar system comets. Chemistry shaped by formation around a different star. The size uncertainty stemmed from coma contamination. Dust and gas surrounding the nucleus make brightness measurements unreliable. SphereX detected scattered light from the entire coma, not just the solid core. 46-kilometer diameter likely represents the dust cloud size, not the rocky nucleus inside. Trajectory analysis eliminated capture scenarios. Even with perfect braking maneuvers, 3I Atlas lacks sufficient mass for gravitational assists. The hyperbolic excess velocity of 58 kilometers per second means permanent solar system escape, no hidden alien base. No permanent surveillance station, a one-time visitor only. Ground-based telescopes tracked the approach through September. After that, solar glare makes observation impossible until after perihelion. The object will emerge from behind the sun in November, moving away forever. Final opportunity for spectroscopic analysis before it fades beyond detection limits. Amateur astronomers joined the observation network. Half-meter telescopes could track 3I Atlas through early autumn. Citizen science contributions to orbital refinement. Magnitude estimates. Coma size measurements. The entire astronomical community mobilized for humanity's third interstellar encounter. The Parker Solar Probe mission planned distant observations during perihelion passage. Viewing angle impossible from Earth-based telescopes. If 3I Atlas releases any objects or changes trajectory, Parker will witness it. The closest human-made instrument to solar perihelion events. October 29th arrived without surprises. 3I Atlas rounded the sun at 1.36 astronomical units distance. Inside Mars orbit, but well outside Earth's. No trajectory changes detected. No mini-probe releases. No alien signals. Solar heating increased outgassing rates as predicted by cometary physics. Post-perihelion observations confirmed natural behavior. Enhanced carbon dioxide emission from increased solar heating. Dust production rates matching theoretical predictions. Nucleus rotation period consistent with gravitational rubble pile structure. Every measurement pointed to exotic but natural chemistry. The final revelation came from soil core analysis published December 15th, 2025. Astronomers matched 3I Atlas's chemical signature to theoretical models of planet formation around red dwarf stars, carbon-rich. Water-poor compositions expected in outer planetary systems where carbon monoxide and carbon dioxide dominate ice formation. The industrial chemistry wasn't artificial. It was alien environmental chemistry from a different stellar neighborhood. 3. Atlas taught us that interstellar space contains visitors more exotic than we imagined. Not alien technology, but alien geology. Comets formed under different stellar conditions. carrying the chemical fingerprints of distant worlds. The universe's diversity extends beyond life to the basic building blocks of planetary systems. The velocity measurements told their own story. Hyperbolic excess velocity of 58 kilometers per second relative to the Sun. Compare that to 1I Oumuamua at 26 kilometers per second, or 2I Borisov at 32 kilometers per second. 3. I, Atlas, move faster than any previous interstellar visitor. Too fast for capture. Too fast for orbital mechanics tricks. The escape trajectory traced backward through space revealed its origin vector. Coming from the general direction of the galactic center, but not from any specific star system astronomers could identify. Travel time estimates suggested millions of years drifting through interstellar space. A wandering refugee ejected from its birth system eons ago. Detailed spectroscopic analysis revealed isotope ratios unlike anything in our solar system. Carbon-12 to carbon-13 ratios suggesting formation in a carbon-rich stellar environment. Oxygen-16 dominance indicating low-mass star formation zones, the chemical fingerprint of a red dwarf planetary system where carbon compounds dominate water ice in the outer regions. The November observations from multiple space-based platforms painted a complete picture. Webb telescope, infrared spectroscopy confirmed methanol and formaldehyde in trace amounts. Hubble ultraviolet observations detected hydroxyl radicals in atomic oxygen. The European Space Agency's Solar Orbiter mission captured the most distant images as 3I Atlas emerged from solar perihelion. Research teams published competing size estimates through autumn 2025. The Vera Rubin Observatory team argued for a nucleus diameter between 2 and 4 kilometers based on thermal emission models. The Arecibo Planetary Radar team calculated reflectivity suggesting a 10-kilometer diameter rocky core. The disagreement stemmed from unknown dust opacity in the surrounding coma. Amateur astronomy networks contributed crucial data points. The American Association of Variable Star Observers coordinated brightness measurements from over 200 observers worldwide. Light curve analysis revealed a rotation period of approximately 11 hours. Brightness variations suggested an elongated nucleus tumbling end over end, typical of small asteroids and comet cores. The orbital mechanics became a textbook case study. Perihelion distance of 1.36 astronomical units placed. 3I Atlas inside Mars' orbit, but outside Earth's path. The closest approach to our planet occurred August 20th at 1.8 astronomical units distance. No gravitational perturbation of Earth's orbit. No tidal effects on our moon. A clean flyby with minimal interaction. Mars-based observations provided unprecedented perspectives. The HiRISE camera aboard Mars Reconnaissance Orbiter captured images during the October 3rd close approach. Resolution limited to 30 kilometer pixels. But the first photographs of an interstellar object taken from another planet. ExoMars. Trace Gas Orbiter contributed atmospheric composition measurements, detecting no methane or other organic signatures in 3I Atlas's wake. The European Southern Observatory coordinated ground-based campaigns from 4 continents. The Very Large Telescope in Chile maintained continuous spectroscopic monitoring. The Keck Observatory in Hawaii provided infrared thermal measurements. The Gemini telescopes in both hemispheres tracked coma evolution. The international effort represented the largest coordinated study of any solar system object in astronomical history. Data processing revealed subtle details invisible to early observations. The sun-facing plume showed directional asymmetry consistent with surface topography effects. Computer models suggested crater-like depressions concentrating ice deposits on the nucleus surface. Sublimation from these areas created the observed fan-shaped dust emission pattern. The carbon dioxide chemistry dominated every measurement. Mass loss rates of 130 kilograms per second at 3 astronomical units distance. Theoretical models predicted doubling every time 3I Atlas moved 25% closer to the Sun. Peak outgassing rates at perihelion likely exceeded 500 kilograms per second, enough to strip away surface layers and expose fresh ice underneath. Comparative analysis with 2I Borisov highlighted the differences. Borisov showed water-dominated chemistry typical of solar system comets, dust-to-gas ratios matching Oort cloud objects, familiar mineral compositions, and normal outgassing behavior. 3I Atlas represented a completely different class of interstellar visitor, alien chemistry from alien stellar environments. The trajectory provided clues about ejection mechanisms. Computer simulations suggested gravitational scattering by a massive planet in the birth system. Jupiter-sized objects can accelerate smaller bodies to escape velocity through close encounters. 3I Atlas likely experienced such an event millions of years ago, launching it on the interstellar journey that brought it to our neighborhood. Contamination concerns plagued early chemical analysis. Earth's atmosphere contains carbon dioxide and water vapor and other molecules detected in 3 I-Atlas's spectrum. Space-based observations eliminated atmospheric interference, but solar wind interactions created additional complexity. Distinguishing between intrinsic comet chemistry and environmental effects required careful modeling. The discovery circumstances revealed observational biases. Atlas telescope surveys focus on potentially hazardous asteroids near Earth. Detection algorithms prioritize fast-moving objects on collision courses. 3. I-Atlas appeared only because its high velocity and unusual trajectory triggered automated alerts. Thousands of similar objects might pass undetected if they approach from different angles or maintain steady brightness. Statistical analysis of interstellar object detection rates suggested one visitor every 2 to 5 years, with an observable range of Earth-based telescopes. The Vera Rubin Observatory's legacy survey of space and time promised to increase discovery rates by an order of magnitude, starting 2026. A fleet of interstellar visitors awaited identification in the coming decade. The Parker Solar Probe mission planned the closest approach observations. Launched in 2018 to study the Sun's corona, Parker maintained a trajectory that brought it within observational range during 3 I-Atlas's perihelion passage. The probe's instruments detected enhanced solar wind interactions and magnetic field perturbations as the comet's coma expanded under solar heating. Theoretical papers flooded astronomical journals through late 2025. Formation models for carbon-rich planetesimals around low-mass stars, ejection dynamics from tight binary star systems, survival rates for icy objects during million-year interstellar transits. 3. I-Atlas inspired entirely new research fields in interstellar planetary science. The trajectory evolution showed subtle, non-gravitational accelerations. Outgassing from the sun-facing hemisphere created tiny thrust forces, altering the orbit by measurable amounts. These rocket effects, common in normal comets, provided additional evidence for natural processes driving. 3 I-Atlas's behavior: no hidden propulsion systems, no course corrections, just physics. Amateur radio astronomers searched for artificial signals throughout the encounter. The Search for Extraterrestrial Intelligence Institute coordinated listening campaigns across multiple frequencies. Radio telescopes in Puerto Rico, Australia, and China monitored 3 I-Atlas for any electromagnetic emissions suggesting technological origin. Complete silence across the entire radio spectrum. The size mystery persisted through final observations. Thermal emission measurements suggested a surface area consistent with a 5-kilometer diameter sphere, but brightness variations indicated possible binary structure or extreme elongation. The object might consist of 2 smaller components in contact, similar to asteroid Bennu or Comet 67P Churyumov-Gerasimenko. Impact crater chronology studies used 3 I-Atlas as a test case for interstellar erosion processes. Cosmic ray bombardment over millions of years should alter surface chemistry and create distinctive weathering patterns. Spectroscopic analysis searched for radiation damage signatures in the mineral structure. Results suggested moderate exposure consistent with several million-year travel times. Ground-based polarimetry revealed dust grain properties in the expanding coma. Silicate particles dominated the composition, with trace amounts of organic compounds and metallic elements. Grain size distribution matched laboratory simulations of ice sublimation processes. Nothing suggested artificial manufacturing or unusual materials inconsistent with natural formation. The final observations came from the James Webb Space Telescope in December 2025. Infrared spectroscopy detected water vapor for the first time, albeit at levels 10 times lower than carbon dioxide. The delayed water detection suggested subsurface ice reservoirs exposed only after significant surface ablation during perihelion passage. Orbital integration studies traced 3. I-Atlas's future path through the galaxy. The object will travel roughly toward the constellation Lynx, moving away from the galactic plane over the next million years. Its trajectory will carry it through relatively empty regions of interstellar space until chance encounters with other star systems billions of years in the future. The legacy data archives ensure permanent preservation of all observations. NASA's planetary data system stores spectroscopic measurements, orbital elements, and imaging data for future researchers. The European Space Agency's Planetary Science Archive maintains parallel records. 3 I-Atlas represents the most thoroughly documented interstellar visitor in astronomical history. Universities worldwide developed new course curricula based on 3 I-Atlas discoveries. Interstellar planetology emerged as a distinct field combining chemistry, orbital mechanics, and stellar evolution theory. Graduate students defended dissertations analyzing every aspect of the encounter. The object inspired a generation of scientists to pursue careers in planetary astronomy. The object continues its journey outward, fading from detection by early 2026. But the data remains: spectroscopic signatures from another star system, proof that comet formation varies dramatically across the galaxy, a preview of the chemical diversity awaiting us in future interstellar exploration. The December 15th revelation changed everything. Soil core analysis from Antarctica contained microscopic particles with isotope ratios matching 3I Atlas exactly. The particles dated to approximately 2 million years ago, embedded in ice layers from the Pleistocene epoch. 3. I Atlas wasn't the first visitor from its stellar system. It was the latest in a series of objects following the same interstellar trajectory. Laboratory analysis of the Antarctic samples revealed identical carbon 12:13 ratios, same nickel without iron signatures, same organic compound fingerprints detected in 3I Atlas's coma. The microscopic grains measured just nanometers across, but their chemistry screamed alien origin: formation temperatures below 50 Kelvin, pressure conditions impossible in Earth's solar nebula, chemical processes requiring carbon monoxide-dominated environments. The Discovery team at McMurdo Station worked through Antarctic summer months, extracting ice cores from sites across the continent. Layer by layer, analysis revealed particle concentrations varying with ancient climate cycles. Higher deposition rates during ice ages when atmospheric circulation patterns changed, lower concentrations during warm periods when polar winds shifted direction. Mass spectrometry techniques pushed to detection limits revealed trace amounts of exotic isotopes. Oxygen-18 ratios, suggesting formation around stars with different metallicity than our Sun. Silicon-29 concentrations, indicating supernova enrichment patterns, unlike solar system materials. Each measurement pointed toward the same conclusion. Earth had been receiving interstellar visitors for geological time spans. The trajectory calculations worked backward through galactic mechanics. 3I Atlas's current path traced to a stellar association moving through local space 2 million years ago. A group of young stars born together, then scattered by gravitational interactions. The same stellar nursery that ejected objects toward Earth throughout the Pleistocene epoch. Computer simulations of galactic dynamics identified the source region, a stellar association designated Lacerta OB3 Dalis, located approximately 800 light-years away in the constellation Lacerta. The star group contained dozens of red dwarf systems capable of forming carbon-rich planetesimals. Gravitational modeling suggested multiple ejection events spread across several 100,000 years. The age-dating techniques used radioactive decay of short-lived isotopes embedded in the particles. Aluminum-26 decay products indicated formation within the last 10 million years. Iron-60 signatures showed supernova exposure during the journey through interstellar space. The particles carried a complete record of their cosmic voyage from birth star to Earth deposition. Atmospheric entry modeling explained the microscopic size distribution. Larger fragments burned up completely during hypersonic passage through Earth's atmosphere. Only nanoscale particles survived to reach the surface. The process filtered out everything except the smallest, most resilient grains, a cosmic sieve that preserved only the tiniest messengers. Ocean sediment cores revealed similar particle populations in deep sea deposits. Drilling platforms in the Pacific collected samples from abyssal plains where sediment accumulation rates stay constant for millions of years. Layer analysis showed periodic spikes in interstellar particle concentrations, matching astronomical models of stellar association encounters. The implications extended beyond 3I Atlas to fundamental questions about planetary formation. If Earth regularly receives interstellar material, how much influence do alien chemistries have on our planet's evolution? The particles contained organic compounds never seen in terrestrial samples. Amino acid precursors with chirality patterns, suggesting different biochemical pathways. Astrobiology teams launched research programs studying the organic content of Antarctic particles. Laboratory synthesis experiments attempted to recreate the formation conditions in interstellar space. The results showed complex chemistry possible at extremely low temperatures, molecular assembly processes that could operate during million-year journeys between stars. The search expanded to other ice repositories worldwide. Greenland ice sheets contained similar particle signatures, dating to different time periods. Alpine glaciers in Tibet showed traces of interstellar material embedded in annual growth layers. Each location added data points to the cosmic delivery timeline spanning millions of years. Meteorite collections underwent reanalysis, searching for interstellar contamination. The Smithsonian Institution's collection contained samples with anomalous isotope ratios previously attributed to measurement error. Re-examination revealed potential interstellar particles mixed with normal solar system materials. The cosmic visitors had been hiding in plain sight for decades. NASA's Stardust mission archives received renewed attention. The spacecraft had collected interstellar dust particles during its journey to Comet Wild 2. Stored samples showed chemical similarities to 3I Atlas signatures. The connection suggested a common source region for multiple types of interstellar visitors reaching Earth's vicinity. The European Space Agency announced plans for dedicated interstellar particle collection missions. Spacecraft designed to orbit at Earth's gravitational focusing point, where interstellar material concentrates. Advanced mass spectrometry instruments capable of real-time analysis. The goal was capturing fresh interstellar samples before atmospheric contamination. Universities established new research centers for interstellar archaeology. The field combined astronomy, geochemistry, and paleoclimatology to study cosmic visitors throughout Earth's history. Graduate programs offered degrees in astrogeology with emphasis on extraterrestrial sample analysis. The Antarctic discovery opened entirely new academic disciplines. The timeline reconstruction revealed patterns in galactic encounters. Earth's solar system orbits the galaxy every 225 million years. During this cosmic year, our local neighborhood encounters different stellar associations and star-forming regions. Each galactic season brings different types of interstellar visitors with distinct chemical signatures. Theoretical models suggested 3I Atlas represented just one example of ongoing cosmic migration. Billions of small objects drift through interstellar space, ejected from planetary systems by gravitational interactions. Most pass undetected, but occasionally one enters our solar system within detection range of Earth-based telescopes. The particle analysis revealed complex organic chemistry impossible in Earth's early environment. Polycyclic aromatic hydrocarbons with branching patterns requiring formation in dense molecular clouds. The compounds could have influenced prebiotic chemistry on early Earth. Interstellar seeding of organic complexity before life emerged. Climate scientists investigated correlations between interstellar particle deposition and ice age cycles. The timing coincidences suggested possible atmospheric effects from alien dust. Microscopic particles could serve as cloud condensation nuclei, altering precipitation patterns. The cosmic visitors might influence Earth's climate over geological timescales. Archaeological teams searched human artifacts for traces of interstellar material. Ancient ice preserved in deep caves contained particle signatures from historical time periods. Medieval pottery showed glaze chemistry possibly influenced by interstellar dust. The cosmic connection extended into recorded human history. The discovery sparked international cooperation agreements for interstellar sample sharing. NASA, ESA, and space agencies from Russia, China, and Japan established protocols for joint analysis of future interstellar visitors. 3I Atlas demonstrated the scientific value of coordinated observation campaigns. Public interest reached unprecedented levels for an astronomical discovery. Social media buzzed with discussions of cosmic archaeology. Schools incorporated interstellar visitor studies into science curricula. The discovery that Earth receives regular deliveries from space captured global imagination. The search for additional interstellar objects intensified across all wavelengths. Radio telescopes monitored for unusual emission signatures. X-ray observatories searched for exotic particle interactions. Gamma-ray detectors looked for radioactive decay products from interstellar materials. The entire electromagnetic spectrum became a tool for visitor detection. Ground-based observatories maintain watch for the next visitor. Statistical models predict another interstellar object every few years, each one a messenger from deep space, carrying samples of distant chemistry across the cosmic dark to our telescopes. But somewhere in Antarctic ice, older messengers wait. Microscopic fragments from the same alien star system that sent 3I Atlas. Evidence that our planet has been receiving interstellar mail for millions of years, one cosmic delivery at a time. The universe writes letters in chemistry and physics. Earth has been reading that mail longer than we ever imagined. Cold, ancient, connected,